The next topic is the energy stored in a capacitor. We know that a capacitor is a device used to store the electric charges, and in this section we will derive an expression for the energy stored in a capacitor. Capacitor simply is an arrangement, that is two conductor plate separated by a distance d. This conducting plate each is made up of neutral atoms. It consists of the neutral atom is represented by this one. A large number of neutral atoms are there on each capacitor plates. Then to charge up a capacitor, we have to remove this electron from the one plate. That is, if I connect this to the positive terminal of the battery and this plate to the negative terminal of the battery, to charge up this capacitor plate, we have to remove the electron from each atom, that is from the positive plate. If this is a representation of a neutral atom and the positive symbol represents the total amount of the positive charges and the negative symbol represents the total amount of negative charges in the atom, and if a single electron is removed from this atom, then there will be a deficiency of the electron. Therefore, this atom is said to be positively charged. Fine. And since the atom is a neutral, represented by this one, total charge is 0. If any additional electron is supplied to this atom, then there will be additional negative charge. Therefore, the total charge of this atom will be 0 minus 1 be negative. That is, this atom is said to be negatively charged. Okay. That is, to charge a neutral atom, what we have to do is we have to remove the electron from the neutral atom. That is, the capacitor plates corresponding to this plate is represented by this way, and this plate is represented by this way. Each conducting plate consists of a large number of neutral atoms, and to charge up a capacitor means here this capacitor should be positively charged, this should be negatively charged. For this, we will connect this setup to a battery. That is, this is the positive terminal is connected to this plate and negative terminal is connected to this plate. If you connect a battery to this setup, then the positive terminal of the battery attracts an electron from this atom or from this plate. Then the electrons will be started to move from this plate. When an electron is removed, this plate will be positively charged and this also positively charged, and the battery carries this electron from this plate and deposits into the negatively connected plate. That is, this plate is connected to the negative terminal of the battery, and if an electron reaches on this plate and this atom is now negatively charged, and another electron if reaches on this plate and this atom is also negatively charged, that is, I can represent negatively charged atom like this and a positively charged atom like this. That is, to charge up a capacitor, we have to remove electrons from the positive plate and carry them to the negative plate. Actually, battery does this job. At any instant, if the charges reaches on this capacitor plate, like as shown in this figure, at any instant there will be a potential difference, and the potential difference is equal to V by C will be there between the capacitor plates. To remove further negative electrons from this charge and to deposit on this another plate, the already reached negative charges will try to oppose these newly coming electrons. That is, there will be a Coulomb repulsion. Then against this Coulomb repulsion, battery has to do certain amount of work. That is, the amount of work done to transport the additional small amount of charge dq to this plate, that is given by dw. dw is equal to V into dq. Fine. In this way, the battery will do a total amount of work that is given by W. For what battery does this work? That is to charge this capacitor plates from 0 to capital Q. Therefore, this W can be written as integration 0 to Q V dq. Then the amount of work done by this battery, that will be stored as the energy in the capacitor. That is, after this amount of work is done, then if you look at this figure, that is here this plate will be positively charged and this plate will be negatively charged. This is the action of the charging of a capacitor. Fine. Now let us note the each steps. That is, to charge up a capacitor, we have to remove the electrons from the positive plate and carry them to the negative plates. If you see this figure, we have to carry the electron from this positive plate and this has to be deposited on the negative plate. In this way, this capacitor is charged. Actually, batteries does this job. That is, during this charging process, the charges already reached on this negative plate, there is the negative charges, that will exerts a repulsive force on the newly charges carried to deposit on these plates. Charges that is already reached here creates a potential difference between these two plates. That potential difference was noted, that is V is equal to Q by C, and to transport another small amount of charge dq to this negatively charged plate, the battery has to do certain amount of work. That work, that is denoted by dw. That is, dw is the work done to transport a small amount of charge dq to the capacitor plate. Okay. Now let me note down this also. That is, at any instant, there exists a potential difference between the plates. That potential difference is given by V is equal to Q by C. To transfer additional charge dq, work must be done by the battery against the electrostatic force that is offered by the already reached charges. Okay, that is the amount of work done to transport a small amount of charge dq. That is given by dw is equal to v dq, where this v is the potential at any instant on the capacitor plates. That v can be written as q by c. Therefore, this w can be written as q by c into dq. Therefore, the total work done to charge the capacitor that is from 0 to capital Q, that can be written as W, that we are going to integrate this above equation from 0 to Q, small q by c into dq. This is nothing but 1 by c into integration 0 to q, q dq, that is 1 by c into q square by 2, 0 to q, that is this w can be written as q square divided by 2c. This is the total amount of work done by the battery. This expression can also be written in this fashion, that is, if you substitute q is equal to cv, then q square will be equal to c square v square. Then this w can be written as c square v square divided by 2c is equal to half cv square. This is the another expression of the energy stored in the capacitor. Both are the expression for the energy stored in a capacitor. Fine. Now let us do a problem. This is a question. Find the capacitance per unit length of two coaxial metal cylindrical tubes of radii A and B. That here we have two cylindrical tubes. One is having the small radius A, that is this one, and another is having the larger one having the radius B. That is here B is greater than A. We have to find out the capacitance per unit length. That is, we have to find out what is the capacitance per unit length. Fine. To find out the capacitance, we have this expression, capacitance C is equal to total charge divided by the potential difference V. Right here, potential difference V can be written as minus B to A, that is from, we are coming from infinity to the central point, that is we are coming from the infinity means from the outer region to the inner region. Therefore the outer region start from the B, inner region up to the A. That is the reference point, that is from this B to A. E dot dr. Then here what is this E? This E is the electric field due to the long cylinder. Electric field due to a long cylinder. What is a long cylinder? That is, if we consider a very long cylinder, this is equivalent to a wire. This is equivalent to a charged wire. That is, charged wire is equivalent to a long cylinder, because the shape and size of the long charged wire, that is similar to that of a long charged cylinder. Fine. That is the charge density is lambda. That is, this lambda can be written as total charge on the wire or cylinder is Q, and its length is L. This is Q by L. Okay. Then the electric field at a distance r due to these charges, or the electric field due to a long cylinder, or the electric field due to a long charged wire, that electric field is given by lambda divided by 2 pi epsilon 0 r cap. Okay. Now what I will do here is, instead of this lambda, I will substitute this Q by L. Therefore, this electric field can be written as minus of B to A. I will substitute instead of lambda Q by 2 pi epsilon 0 r, and L is the r is there, then Q by L to r dot. This dr can be written as dr r cap. Okay. There is this electric potential. That is, I will write here. I can take the constant term outside. Is minus Q divided by 2 pi epsilon 0 L integration from B to A, then r dot this r, that will be 1, this will be 1 by r dr. This is equal to Q by minus Q by 2 pi epsilon 0 L, and the integration of 1 by r dr, that will be natural log r B to A. That is minus Q by 2 pi epsilon 0 L into natural log A minus natural log B. If I take the minus sign inside, this will be Q divided by 2 pi epsilon 0 L natural log B divided by natural log A, or we can write Q divided by 2 pi epsilon 0 L natural log B by A. This is electric potential. Then here I can write this Q divided by, instead of this V, I can substitute this one. This is Q divided by 2 pi epsilon 0 L natural log B by A. This is the capacitance C. Here this Q and Q get cancelled. Then we are left with C is equal to 2 pi epsilon 0 L divided by natural log B by A, or capacitance per unit length. That is, if you see the question, capacitance per unit length, this was our aim. That is, this is C by L, that can be written as 2 pi epsilon 0 divided by natural log B by A. This is the final expression for the capacitance stored in a cylindrical cylinders having the radius A and outer radius B. Okay, where B is the outer radius and A is the inner radius.